does this work? That's this thing. Yep. Okay. Thanks for coming, and thanks to the organizers for arranging this meeting. This was a fun opportunity. So I'll be continuing with the same sort of material as Noah, working with the multi-species coalescent, and I'll be looking at consequences of that model for consensus trees, and in particular when consensus trees are generated from independent gene trees and thought of as a way of estimating the species tree. Okay, so I'll give very brief background on species trees versus gene trees, since Noah did that, and the types of consensus methods that we'll be using. So we'll be looking at 3 different consensus methods. And I'm going to introduce this concept of asymptotic consensus trees, which are consensus trees that are generated from gene tree probabilities rather than from actual data. And we'll look at the asymptotic case when the number of genes is going to infinity, theoretically, and also finite cases, so finite numbers of loci. And finally, I'll end with some consistency results for the 3 different types of consensus methods. Okay, so we should all be used to this kind of idea by now. If you go along the genome and look at different genes, you're going to find different gene trees that are all correct, even though you expect there to be one true speciation history. Okay, and Noah showed slides like this also. So I'm, again, only looking at incomplete lineage sorting as an explanation for gene tree conflict. Of course, there are other types of gene tree conflict, but the incomplete lineage sorting is very easy to model using the coalescent, so we can explore very detailed consequences of what gene tree frequencies are expected to be. Okay, so again, the different gene trees that result from incomplete lineage sorting, they're all correct descriptions of the gene histories. So we don't have to think of them as being due to any sort of estimation or sampling error. And I'm only going to consider gene trees that are considered known for this talk. So I'm not going to talk about problems dealing with tree reconstruction and mutation and that sort of thing. So as Noah talked about in the previous talk, the gene tree discordance in this model depends on the branch lengths in the species tree as well as the topology. And the branch lengths are measured in the number of generations scaled by the effective population size. And because of this parameter has these 2 terms jointly, we only care about the ratio. We don't actually care about the particular population sizes. So we can't really tell if the population sizes are changing. So we only assume that population sizes are constant within populations, but between populations they're allowed to vary. Okay, so here's another way of visualizing what these distributions look like. So this is 4 taxa. These are all rooted trees. And there are 15 different topologies. And for these 2 branch lengths in this model tree, these are the probabilities. So I chose this y equals 1.2. This was based on a paper of Ranella and Yang, where if you took their point estimates for divergence times between the gorilla divergence and the human-chimp divergence, if you took a ratio of their estimates, you get 1.2. So there's a lot of uncertainty in that estimate, but that's why I chose the 1.2. So this is just sort of to mimic the human-chimp gorilla tree. And for these branch lengths, we get about a little over 70% of the matching tree, 70% probability that the gene tree will match the species tree, and roughly 10% for these other trees, which if you relabel this as human, chimp, gorilla, this would be with human and gorilla and chimp and gorilla. So this is actually pretty close to, yeah, it's very close to the talk that you gave the other day. Anyway, so that's what motivated the choice of those branch lengths. So anyway, so this seems pretty relevant for modeling incomplete lineage sorting in real examples. Noah and I are also interested in some more extreme examples. So this might not be relevant for the human chimp gorilla case, but it's still very theoretically interesting, and it might be more relevant for cases where you have larger population sizes or you have rapid speciations, such as in a rapid radiation. Okay, so in this example, both branch lengths are 0.1, and here is the gene tree matching the species tree. You get a probability of slightly over 10%. This is the tree with C joining with D before joining the A and B lineages. So that has a slightly higher probability of about 13%. So this is a case where there's one anomalous gene tree. And these other two symmetric trees are also highly probable, just slightly less probable than the matching one. And if you reduce these branches down to, say, 0.05, this probability will go down a little bit, these two will go up, and you'll end up with that situation with 3 anomalous gene trees, and the matching tree being the 4th most probable. Okay, so this gives you an idea of how much variability you can actually get in these distributions. So one thing to do with all of these different trees that we expect is to perform a consensus method. There are other things you can do, such as concatenation, and I've looked at that also, and well, that can perform poorly when you have sequences generated from different topologies. So a natural question to ask is, well, what happens with consensus methods instead? So a consensus method is a method of combining trees where you have a set of input trees. So in this example, there are 3 trees. And just using majority rule, A and B form a clade in 2 out of the 3 trees. So it's more than 50% of the time. So it ends up being in a majority rule tree. And there are other consensus methods that we can consider. But I want to think of a consensus tree as a function of the input trees, and in particular we can think of it as a function of the frequency with which each input tree occurs. So you're allowed to have input trees be repeated, and that can change the outcome. Okay, so possible types of consensus trees. This isn't exhaustive by any means, but it's some of the more common ones. So a strict consensus tree, only clades that are included in all of the input trees are included in the strict consensus tree. So that's not going to be very interesting for us because we're interested in cases when there is a lot of gene tree conflict. And in that case, the strict consensus tree is usually just going to be a star tree. Okay, so we didn't really look at that. Democratic vote tree, I don't know if that's really standard terminology. I think I got it out of a Dawkins book. But it's taking the gene tree that occurs the most frequently. So from Noah's talk, we can see that the most frequent gene tree doesn't necessarily match the species tree, so this is not going to be a consistent method for estimating the species tree. Okay, so these 3 methods seem more interesting for our purposes. So majority rule, this is probably the most popular. This is the tree that has all the clades that were observed in strictly greater than 50% of the trees, of the input trees. Greedy consensus, sometimes in the literature people are doing greedy consensus, but they say they're doing majority rule, so you may have heard about it that way. But the idea is that you rank clades by their proportions that they occur in the input trees, and you go through one at a time and you accept the most frequently observed clade, put it into the consensus tree, and cross off all the clades that are incompatible with it, and then repeat that procedure until you end up with a fully resolved tree. At times, the most frequently occurring clade, there might be a tie, and then you have to randomly do a tie break in order to end up with a fully resolved tree. Okay, and finally, R-star trees. So these are probably the least well known. But for each set of 3 taxa, you can find the most commonly occurring triple. So if we look at just the taxa A, B, and C, for example, we can see which of these 3 relationships occurs the most often, which is the most often displayed in the full tree. And you can build the tree from the most commonly occurring triples from all n choose 3 sets of 3 taxa. Okay, so as I mentioned, I'm interested in what happens if you have a very large number of gene trees. So ordinarily, consensus trees are computed from data sets, so trees that were obtained through some estimation method or something like that. So you can think of those as statistics. So I don't want to think of gene trees that way. I want to think of them instead as a property of a gene tree distribution. So I'm going to replace sample proportions of gene trees with the proportions that you'd expect under the coalescent model, and just use those theoretical probabilities instead of actual sample proportions. And one motivation for doing that is if you have a large number of independent loci, the proportions of gene trees that you observe, assuming your reconstruction method works correctly, should approach the proportions that you'd expect under the coalescent model. So that's a motivation for doing it. Okay, so here's an example, again, using 4 taxon trees. So there are 15 4-taxon trees, and I'm just calling their probabilities P1 through P15. And here are 2 sets of branch lengths that I'll use as examples. So here are those probabilities, pretty similar to what Noah showed. So both of these cases have anomalous gene trees. This highlighted tree is the matching tree probability, 0.104. The anomalous one has probability 0.128. So you can get the probabilities of clades by summing the probabilities of all gene trees that have those clades. And that's just going to be a sum of 3 genes for each, 3 gene tree probabilities for each clade. And for all of these, you see the probability of each clade is less than 0.5. So the majority rule is just going to be a star tree, because there are no clades that have greater than 50% probability. The greedy consensus tree, however, we begin with the clade that occurs with the highest probability. That's 0.332 in this example, 0.275 in that example. So the greedy algorithm will accept AB as a clade, even though it occurs with less than 50% probability. And that matches the species tree, so far so good. So next we eliminate clades that are incompatible with AB. So if AB is a clade on the tree, these other clades can't be. So they're not going to be in the greedy consensus tree. So there are only 3 other clades to consider next. And for the branch length of 0.1, this 0.215 is the next highest probability clade. That's the ABC. So for this set of branch lengths, the greedy consensus tree is going to have AB and ABC as clades. And that means that the greedy consensus tree will have to be this tree, and the algorithm is done. And that matches the species tree. And that's kind of impressive because there's an anomalous gene tree in this case, and the greedy consensus algorithm was able to recover the correct species tree even in a setting where there was an anomalous gene tree. So that's not bad. So however, if we go to a smaller branch length and do the same algorithm, again we get the AB clade with the 0.275, but then these 2 switch orders in terms of their probability, and the CD clade becomes more probable than ABC. So the gene tree or the greedy tree has to have AB and CD. So this ends up being the greedy consensus tree. So if you make the branches extreme enough, the greedy consensus tree is going to fail to recover the correct tree in this case. Okay. Okay, so the R star example. So using the same set of branch lengths, you can get the probability of a rooted triple by, again, summing over gene trees that have that rooted triple. So for example, if you're considering the A, B, and C taxa, putting A and B together in a clade that has probability 0.36, and putting either AC together or BC together will have probability 0.316. So the R star consensus tree should display this rooted triple of A, B together in C. And if you do that for all sets of 3 taxa, these are the favored rooted triples. And regardless of the set of branch lengths you choose, you recover the underlying species tree using this R star method. Okay. So using the same set of frequencies, all 3 methods recover different trees. The majority rule tree was just too conservative and wasn't able to commit to any clades. The R star tree did a nice job of recovering the right tree, and the greedy tree fumbled a bit when the branches were short enough. Okay, so analogous to the anomaly zone that Noah talked about, we can create, or we can determine regions in the parameter space where the majority rule tree, which is this left plot, is going to be unresolved. So this dark line here is the border of the anomaly zone that Noah showed in the previous talk. And the shaded regions show different majority rule trees that result in different parts of the parameter space. So this region is fairly large, and again, this means that even if you have an infinite amount of data, majority rule is not able to fully recover the tree. On the other hand, the tree that it does end up with is consistent with the species tree in the sense that the species tree is a refinement of any of these trees. So the majority rule tree is conservative and not able to fully recover the tree, but it has a nice property that it doesn't give you any misleading clades. Okay, the greedy zone, or the too greedy zone we call it. So this is the part of the branch length space where the greedy consensus algorithm returns the wrong tree, again using that 4-taxon model species tree. Okay, so the two blue regions are places where the greedy consensus tree returns the symmetric tree when it should be the asymmetric tree. And it turns out that this region is strictly a subset of the anomaly zone. In this case, the anomaly zone is strictly a subset of this unresolved zone for majority rule. And it's an open question for us whether, if we move to more taxa, whether these subset relationships will hold or not. We don't know. Okay, so those examples were the asymptotic cases when the proportions of each gene tree matched the expected proportions under the coalescent. So something that might be more biologically relevant is if you have a finite number of samples, a finite number of loci. I'm running out of time, so I'll go through this quickly. But the idea is you can enumerate all possible samples of a given size. And this can be done using a multinomial, where the number of categories is the number of gene tree topologies. And the probability that a consensus function of the gene tree frequencies returns a particular tree is going to be the number of multinomial samples that return that tree weighted by their multinomial probabilities. Okay, so here are some plots of those situations. So this is for samples of up to 25 loci. So here's an example where majority rule is recovering the correct tree, but it's very slow to do so. So it only has about a 0.4 probability, even with 25 loci. And then when you make the branch lengths smaller, it's increasingly likely to return the star tree. That's the black circle. For the other methods, R star, in all cases, it's these red squares that represent the matching tree. So it's increasingly likely to recover the matching tree. It is very slow to do so, however. So when there's a lot of gene tree incongruence like this, it's actually more likely to return this partially unresolved tree than the matching tree for up to 25 loci. And both of these are increasing with the number of loci. So we only have a theoretical result that says that eventually it's going to return the true tree. And we only computed this up to 25 loci because the number of terms in that multinomial sum is 15 billion. And I tried going up to 35, but it took 2 months because that was like 675 billion terms in the sum. So, okay, and then here's greedy. And so greedy is consistent here, but takes, or it recovers a true tree eventually, but takes a number of loci to do so. And here's the region where greedy returns the wrong tree. Okay, so the finite plots were just sort of illustrations. The main results are the theorems about the asymptotic cases. So for majority rule, the results I showed for 4 taxa apply more generally. That the majority rule asymptotic consensus trees do not have any clades not on the species tree, so they can always be unresolved if you choose the branch lengths right on the species tree, but they're never going to have clades that are incorrect. They just might not have as many clades as you would like. Greedy asymptotic consensus trees, we just showed 4 taxon results, but we have the more general result that with more than 4 species, you can always find branch lengths that make greedy consensus return the wrong tree. And the proof and the intuition for this are very similar to the proof that anomalous gene trees exist for all species trees with more than 5 taxa. It's an inductive argument again. Okay, so finally, the R star asymptotic consensus trees always match the species tree, regardless of the species tree topology and branch lengths. So that's a nice result for the R star trees. And we haven't investigated actually using this to infer species trees when you have sequence data and all of that messiness. So, and we don't also have results on how quickly it converges to the right tree. So we don't know in practice how good of a method that would be, but that's the next step to investigate. Okay. So in conclusion, these gene tree probabilities, they're useful for a lot of things, but in this context, they're useful for understanding asymptotic behavior of consensus trees. Greedy consensus trees can be misleading, but it might have been hard to tell this from the plot, but often they outperform the other methods, including R star, in terms of the speed of getting to the right tree when you're not in the too greedy zone. So it actually does pretty well in practice, even though R star is more robust. And the R star consensus trees are consistent, and there wasn't much time to show this also, but they do outperform the majority rule, even in cases where majority rule recovers the correct tree. So, so I'm not sure why the R star trees are not used more often. They seem pretty good. Okay, so.
Do you have any intuition as to why the R star method kind of avoids the anomalous gene trees?
Yeah, so for anomalous gene trees only occur if you have 4 or more taxa. So the R star idea is to use probabilities of these rooted triples. But the highest probability rooted triple is always displayed by the species tree. So if you can get all the rooted triples correct, then you can get the species tree to be correct. That's the main idea. Mm-hmm.
So maybe one comment, we have also studied these things using sort of a variant of the tree puzzle algorithm.
Mm-hmm.
Just use rooted triples, and if you then go to lots of more sequences, then your R star method is always superior to all the other methods we discussed. But you need really lots of genes.
Yeah, right.
So it's not like 25, it goes up to 200,000 if you have a large tree,
right,
with these weird sort of branch lengths.
Right. Yeah, I can believe that.
I can show you the results.
Okay, that would be great.
Okay, well, let's think.